This is the Lightning Junkies podcast with your host, Chaz. On this special episode of the podcast, we have a guest co-host, and that co-host is Shinobi. You might know him from episode 11. He's back on another Lightning Sucks episode. Lightning Sucks 2 Electric Boogaloo. We have Elias talking about Lightning Network privacy, and specifically the paper that he helped to co-author, in which he discussed correlating latency in order to identify people on the Lightning Network. We go into these topics and more. Just to make sure it's clear, all of this is tongue-in-cheek. I don't actually think the Lightning Network sucks. People on Twitter are already getting it twisted. Let's just be clear, I love the Lightning Network. I use it practically every day. I've used it multiple times today already. A couple of other notes before we actually jump into the show. We've released our first newsletter. We're going to do that the first Monday of every month. We definitely invite you to subscribe to our mailing list. Our mailing list will not only have the main newsletter, which we are currently calling Junkies News Alpha. It will also have what we're currently calling Cat's Corner, which will have Lightning Cat's newbie adventures in the Lightning Network, so that the newbies out there will have someone they can identify with, learn little tidbits from, and be able to grow and learn with. You can start getting some of that written Lightning Junkies content by going to lightningjunkies.net/sign up. If you visit us at lightningjunkies.net/support, you'll see the various ways that you can support us here at the show. You can follow us on various podcasting platforms. You can chip in Bitcoin and Bitcoin over Lightning. You can even do so with Strike. You can share us on social media. All kinds of different ways that you can show your appreciation for the show and for the content that we create here for you. If there are any sponsors out there, we feel like we have a strong pitch for why you should sponsor us. So don't hesitate to contact us at chaz@lightningjunkies.net. And I'll follow up with you. We are continuing to grow here on Lightning Junkies. Our ultimate goal would be to be able to appeal to as many different audiences in the Lightning Network ecosystem as possible. Right now, we're generally appealing to as many audiences all at once. But I think the ideal would be being able to appeal to newbie users. We're going to start releasing as much newbie-focused content as we possibly can, with the main Lightning Junkies show probably still being more technical than the rest of the content that we're going to have, with Cat's Corner being an example of some of the more newbie-focused content, as well as a new show that we're going to be releasing soon as well. We want to encourage the tinkerer. We want to encourage the builder, the coder, the person making art, whatever. I can't name all the things, but I'm sure you can, use your imagination, get inspired, and start figuring out what you think that might be for yourself. An easy example was the amount of people getting inspired after the Ben Arc episode, in which a lot of people bought the M5 stack or otherwise started developing things for the M5 stack and just having fun and otherwise contributing to Bitcoin and the Lightning Network, learning in a more hands-on way. That's something we really want to encourage around here. Last, we want to do everything that we possibly can to encourage already working developers outside of Bitcoin and outside of the Lightning Network to be able to jump into Lightning Network development, be encouraged, be inspired, and maybe build something that will bring more people in and build that feedback loop. That's the kind of podcast that we want to be, giving that Lightning Network education, Lightning Network entertainment, Lightning Network inspiration, and Lightning Network practical tips, tricks, all these things and more. So if you wish to see us expand any more, we hope that you'd be willing to support us in the ways that we've already mentioned. So now all that fun stuff is out of the way. Let's go ahead and jump into this amazing episode. I'd like to go ahead and introduce on this special episode of Lightning Junkies Shinobi as our co-host, and I would like to go ahead and welcome Elias as our guest here.
Hey.
How are you guys doing today?
Hi, how are you doing?
I'm doing good.
Fantastic.
I feel weird being called a co-host on somebody else's show.
Right. Well, hey, it's a new thing for me. I don't think I've ever really had a co-host either, so we're just going at it full speed here. Just to get us started, I wanted to get Elias on the show because he and I can't remember the other gentleman's name off the top of my head. I'm sorry.
Florian George.
Yeah, thank you for that. Wrote a paper about some timing attacks, I believe, kind of boil it down a little bit, that could threaten Lightning Network privacy. Would you call that an accurate little summary there, Elias?
Yeah, that's correct.
Okay, perfect. I wanted to get Shinobi on here because he recently had an episode on Block Digest, episode 226, where he went into this a bit. And we were talking about this, and I felt like it made a lot of sense just to get someone that actually wrote the paper to jump on board the podcast and give us more detail, go back and forth, ask, is Lightning dead? As our listeners see on this episode title, I'm going to name it Lightning Sucks 2 Electric Boogaloo. Right. It's going to be funny on that end, but be clickbaity, trolly thing. But I am concerned about Lightning. I am concerned about the privacy of Lightning. I wanted to get into that. But first, before we really get into the meat and potatoes of all that, I wanted to get a bit of your background, Elias, because our guests already know Shinobi, I hope. And if not, they can definitely go back to his episode and listen to that one. That one was pretty amazing. But we're going to skip the background introductions of Shinobi, and we're going to assume people know who he is for now. I would love to get your background, Elias. If you're into Bitcoin, if you're into Lightning, I honestly don't know. If so, how you ended up getting into those things, how would you ended up getting into payment channels and things like that?
I'm a PhD student actually at TU Berlin. My main focus is blockchain technologies, Bitcoin, and payment channel networks is one focus of mine. My main research interests are basically security and privacy, and I'm always looking at it from a networking perspective because that's kind of how I got into that all. To answer the second part a bit, I've been interested in privacy enhancing technologies and in distributed systems basically, or peer-to-peer systems for quite a long time, more or less privately and during my studies of computer science. I think it had to be 2012 or 13, I'd say, when I heard first of Bitcoin. It seemed to me like a pretty neat little idea coming from really being interested in peer-to-peer networks and all the file sharing, but also the technology actually behind file sharing. Back then, being interested in secure messaging, privacy, enhanced messaging, such like OTR messaging for XMPP back then, which is now mostly dead and replaced by something like Signal. Then I stumbled across Bitcoin. I think it was even in a seminar when we talked about it back then. It seemed like a neat little idea, but it didn't think much of it actually at first because it wasn't huge back then. It seemed a bit interesting, but also a bit weird idea. And I kind of shrugged it off at first because I thought, okay, this only would work if enough people are actually using it. Why would you transact with anybody if nobody else is using this payment system? So I kind of shrugged it off and it's like, okay, neat idea, let's move on. I wouldn't say I forgot about it, but I didn't follow it closely and all the development closely. By the time of 2015 or 2016, I stumbled across it again and caught up a bit. 2017, when I had finished my studies, I started my PhD with Florian George at TU Berlin. And since then, I'm focusing my research on blockchain and on Bitcoin. That's how I ended up in the space.
You said that your PhD is in payment channels. What made you pick that particular focus above anything else?
I think in 2017, when I started, payment channel networks were not that common. I think at the time, Lightning, actually implementation was just starting. It was an interesting research area because we found that there are these new types of networks, and coming from, again, computer science and computer networking background, a lot of challenges seemed to arise that were quite similar to the problems we usually face in computer science in the computing networking area, and always a bit differently. For example, our first paper was discussing a route selection algorithm. So basically a routing algorithm. How can we find routes in a network efficiently and most efficiently apart from using something like the currently used source routing so that we can increase the actual success rate without blocking? One area we discussed back then. It turned out that a lot of these issues are quite similar, but you couldn't just apply all the concept of computer networking because because these payment channels have quite different qualities. So, for example, the capacity limit for each channel introduces quite a different problem space always. So it's, for me, a really interesting research topic also, apart from actually technology now getting used. And it's really a neat scaling technology for Bitcoin. It's also a fascinating research topic because it's kind of familiar, but it's a completely new area of research, basically.
Would you say that you're interested in the Lightning Network beyond an academic level, or is it mainly just something that you're interested in and researching, and that's the end of your involvement there?
I've been interested in the whole peer-to-peer technologies and also in Bitcoin for a long time. I'm also personally interested in payment channel networks, or Lightning in particular, because I think they are one of the most promising ways towards scaling, actually, and getting these kind of systems ready for some kind of larger adoption. I think there's no way around that right now.
Before we get into your paper or any of the other papers that are floating out there right now, do you think that there are any obvious problems with the Lightning Network that have not been addressed yet?
That depends on what you mean by that have not been addressed yet. There are challenges that are openly discussed in the community, such as pathfinding, the whole scaling, even on-chain, basically. So what we saw in recent weeks with some attacks basically on HTLCs, that some papers that are looking into what happens if you would try to settle a lot of channels at the same time on-chain. Could you steal funds? There are these challenges that are right now discussed, but they are getting addressed as they come up. And some, as far as I heard from it, they are openly discussed and there are known issues, but the developers are constantly working towards mitigation. I think it's still some way to go until it's really, really rock solid, everything, but it's constantly being worked on. I think that's the answer as far as I understand it.
Would you say that you're optimistic about the Lightning Network actually going global or going mainstream, or whatever metric you want to use there?
I think that's generally out of my area of expertise. I cannot predict the future. So I cannot only say things about the technical level, not so much on how it will evolve in the future. I don't know how adoption will go.
Fair enough. I guess I was mainly asking about your naive sense of it, not necessarily asking you to make a prediction. That's fine. I guess I'm trying to get a clear picture of, do you use the Lightning Network? Do you use Bitcoin? Is it a big part of your life? Or how involved are you, would you say, in this beyond writing papers and things like this?
Are you a stranger or are you one of us?
I mean, I'm doing a PhD on that. So that's currently a really big part of my life, I'd say. Like a lot of time goes into all these research topics. I try to use Bitcoin when I can, basically. With Lightning, personally, I found it a bit hard because the adoption is not there yet, I guess. There are not many outlets for using it actually as a user. I've, of course, played around with it for quite some time.
I would probably agree with that. I think when Strike came out recently, I was complaining on Twitter that Strike is cool and everything, but there's hardly anything on Lightning to bend your Bitcoin on. That it's one or two things that are pretty solid and the rest are toys that are fun, but aren't really going to make anyone coming into the space flip their lid or be really floored by this cool product. Being able to feed chickens is cool, but I don't think anyone is really going to care after the first couple times of doing it. We are going to get into this paper here. I want to get more background on your general sense of things. Do you think if Lightning Network were to fail or were to otherwise be demonstrated to be a dead end, do you think payment channels in general would be a dead end? Do you think if one fails, it doesn't necessarily mean that payment channels altogether are done? Would you agree with that?
Yes, of course. Right now, the Lightning Network is the biggest implementation, I would say, of any kind of payment channel design. Of course, there have been different proposals for different designs. Even if the Lightning Network, with its current design decision, won't work out, the technology itself and the knowledge behind it, that is, of course, kept for the next iteration. I actually doubt that it would fail on a big scale. I could imagine that the adoption doesn't get there, but again, I cannot predict the future. But of course, that could happen. I don't know. From a purely technical level, I don't see the big things that could make it fail. Okay, maybe I shouldn't say it like that, but I'm not entirely sure why it would at this point in time, exactly.
I think you and me are probably of similar mindsets, Elias. My attitude about it isn't so much a worry about failure. It's just about getting pigeonholed more and more due to shortcomings. You know what I mean? Like, it might not wind up being good for use case A and B, but it could still do a really good job for C.
Yeah, that is exactly the point. Maybe Lightning will more be, for example, a backbone for some kind of payment system and not something that is actually directly used by an end user or so. Again, that's getting really speculative. So I'm getting cautious there because we'll just see how it evolves. To kind of directly answer your question you put out there, I don't think Lightning is dead with respect to our paper or right now from any other insights into it.
I appreciate that answer because that got to the core of where I was coming from. I guess failure wasn't the best way to say that.
I can explain why I especially think that it's not that, why I think that. Maybe also coming a bit more to the paper. In recent years, there have been quite some attacks on the privacy of the main Bitcoin network. We had attacks on the consensus layer, on layer 1 basically, and attacks on layer 0, which is the networking layer. We had correlation attacks on the transaction level. People analyzed which transactions match to which transactions and who could this address belong to. There were, of course, the possibility, at least, for network nodes that could observe network messages and could observe where transactions first were announced in the networks. This was partly mitigated by something like trickling and more recently something like Dandelion that tries to counteract these kind of networking attacks. With respect for, especially to our paper, in Lightning, you have to see that Lightning is taking all these transactions off chain and thereby directly increasing privacy guarantees, just due to the fact that the state transitions are negotiated locally instead of globally. Essentially, this entire first area where you could do de-anonymization attacks on privacy, we analyzed the blockchain itself and how transactions are correlated with each other. That is completely gone, this opportunity. You could argue that the channel structure itself, which user connects to which other user, gives something away, but I would argue that is so much more coarsely grained that it doesn't really give you a lot of information about the actual transactions occurring. And so that is probably not a real threat to some kind of privacy. This is basically the first understanding that our research is only, quote unquote, focused on the second part of these privacy attacks, because the first part are by nature mitigated by the Lightning design, because you cannot do any kind of chain analysis. We are only talking about more or less these attacks on the networking level, even if they sometimes not directly happen on the networking level of Lightning.
Could I get your quick opinion on how private Bitcoin is right now, in your opinion, if people use all the tools they have at their disposal, not counting Lightning in this case? Do you think you could be pretty private on Bitcoin at this point?
That's a really hard question to answer, actually. Coming from research, we always try to model our adversaries. We try to state what kind of adversary do we assume? What do we assume that the adversary is capable of doing? If there was such an adversary, what would this result in if the adversary would be to run an attack? You cannot answer what is the privacy of Bitcoin, because it always depends on who's your adversary. If you're looking into a specific, state actor, or if you're looking into maybe just another person that wants to know what you are doing, that also depends a lot on your personal Opsec. If you're always using fresh addresses, if you are willing to pay for something like CoinJoin, it's really hard to give a general answer to that. It really depends on the specific attack case, basically. Let's put it this way. I think I'm currently not aware of any specific attacks on CoinJoins, for example. There are some CoinJoin schemes that are more private than others and are holding against different adversary models. I'm not aware of something actually running an attack on it.
I do appreciate your very scientific response here, not wanting to go too far or not to give too general of a statement. I probably didn't mean if the NSA is trying to get information on what I'm doing, they're probably going to get it. If we take it a couple notches down, let's say, and say if, maybe not the NSA, but maybe the state police in the state that I happen to live in the United States is not going to be able to figure out much about what I'm doing with my Bitcoin, let's say. I think what you're saying is it's pretty solid at this point, that there isn't any well-known thing that would destroy CoinJoins or otherwise destroy any of these other tools that seem to make the linking of people with chain analysis a lot more difficult.
Yeah, at least I'm not really aware of something like that. But of course, that always would mean that you would run all the bells and whistles and do not have some kind of slip. I think it's getting easier to use these technologies or use these ideas of CoinJoin also for some kind of users. But I think in generally, Opsec is really hard. You always pay in some way or form towards some kind of Opsec. If it's only by time that you invest, if you want to be really anonymous, you would always have to run on Tor and always use some kind of VPN, always do everything with CoinJoin and never basically use any kind of address that is associated with your person. I think getting it all right is really hard. That's basically the point. When you slip up, it's probably enough to slip up once if you really have a powerful adversary in mind.
This is the double-edged sword about academics. You think so rationally, systematically, you look at the threats from an objective lens. Dude, we just want statements of fact, okay? Is privacy broken or is it not?
Yeah, well, I think it's, again, the answer is more complex, but in general, I would say no, but it depends.
Thanks, Shinobi, for cutting through and just asking the direct question there. So we're going to keep on going here, I think. I definitely want to get into the actual paper. Shinobi, do you want to set up the basic explanation, a little bit more involved than my explanation of timing attacks? Because I feel like that's very basic and very general. Do you want to introduce it and then have Elias verify and go into it a bit more here?
Let's try to put this as simply as possible, and I'm probably going to skip past maybe some of the subtle aspects of it just to keep it as newbie friendly as possible. When you're routing a payment through the Lightning Network, there's going to be a latency from sending a message off and getting a response back. By the nature of what Lightning is, you kind of know what operations all of the hops in that are doing. Imagine you have a big, well-connected routing node in the middle. You can route a payment that goes one hop out and intentionally craft it to fail, and then see how long it takes to get that response back. And then you can do one down the same path, 2 hops out. And by subtracting the first latency for that first hop, you can figure out the same for the second hop. You can do this for 3 hops and then 4 hops and pretty much map out the latency that it takes for each node in the network to perform a channel update when you're trying to process a payment. Kind of make a map of the whole network in terms of those latencies. From that point, when somebody goes to route a legitimate payment through you, you can use that latency map in addition to things like the CLT V timeout to see how many hops there are, at least from your point. You can kind of just brute force, depending on how long that payment is taking to happen, which likely endpoints are involved in that payment. So when the payment comes through you, you can look at this map of the network that you constructed ahead of time and have a pretty good chance of figuring out which 2 people in the network were paying each other. Would you say that's an accurate TLDR?
I would generally say so. Yeah, I think that's quite a good summary, actually. Maybe we can step a bit back, because I would even start a bit earlier, because the idea of Lightning is, of course, that you build up these HTLCs to route over intermediary nodes, or to be able to route over intermediary nodes with whom you don't have a direct channel with. Even when we leave our timing attacks or the timing attacks we discovered out of at first, we can see that intermediary nodes can observe payments and can, from that observation, gain some information about who probably paid whom, even without running these kind of timing attacks, just by having a look at the channel graph and just by having, for example, as you said, the time lock delta value, also the actual amount of the payment, because that directly excludes a number of channels from the anonymity set. To contextualize that term, in privacy enhancing technologies, we're always talking about the anonymity set. That is the set of all possible senders or receivers in this case. Optimally, the anonymity set of the Lightning Network would be the number of all nodes, because we simply cannot discern them. We don't know who's sent to whom, and our anonymity set would be the number of all nodes. Your chance of being identified correctly would be 1 over n, the number of all nodes. Then what these types of attacks generally do is try to reduce this number of possible candidates that could have sent or received a payment. And even before we get into the timing attacks, this is what intermediaries can do based on the amounts and the time lock value, simply because if you see a payment that has a really high amount, it could not have been routed over channels that have less capacity than this amount. And also, if you see a certain remaining time lock value at a specific point in the network, you can exclude all channels that would require a higher time lock than the remaining value. So these are initial steps, these kind of reductions of the anonymity set. What our timing attacks now do, in addition to these kind of reduction in anonymity set, we try to assign each node a probability that they are the sender or receiver of such an observed payment. The adversary model I talked earlier about in this case would be that we have an adversary which controls a number of nodes in the network. So she's a node operator, basically. These nodes are malicious and they are recording every payment that is sent over them. By having these observations, we then try to assign a probability who is the most likely to have sent this payment. The specific method we do that is our timing attack you just outlined. I just wanted to go one step back.
I think that was a good call. I just jumped right into the logic of building that network map to try to be clear with it. You make a real core point jumping back to the initial building blocks that you guys built on. Because that's the rock in the hard place trade-off with the Lightning Network is you gain a lot of privacy by lifting all of this off chain, but you also have to give up some of that privacy because the very nature of a routed payment channel network like this is there have to be tables with some information to be able to even try to construct a route through it.
Currently, of course, the Lightning Network employs something that we call source routing. That means the node in the network that sends the payment is determining the route the payment should take through the network and constructs all the onion messages, which in terms of privacy is actually a good thing that it determines all the route. So the user itself can determine how the payment should be routed. Also, the user can construct these Sphinx messages, so the onion routed messages that actually increase the privacy quite a bit. Also, why this kind of scheme, the Sphinx scheme, that the onion scheme is used, is that the intermediary nodes should not know or should not be able to determine who sent to whom, because to them, all the messages in the network from their structure are basically looking the same, even if they are transferred over multiple hops, because they cannot see how far the network messages still have to go or how far they already went before the intermediary observed the message. The timing attacks are aiming at exactly that. We try to infer how far away we are in the network from the source or the target of a payment, or how far these network messages have to travel in the network and are coming back to us. If you are picturing a network graph in your head and you're thinking of all those nodes that are interconnected, you could say we try to first drop all edges that are not possible. So we exclude all the edges that the payment couldn't have come from or couldn't go in the future after we observed it. Then we try to draw a circle around our node by having this timing bound. That way we can see, okay, who is left in our candidate set? And then we, through our algorithm, rank them, which one is the most probable left in this circle of nodes that is around our node in the network.
Should I force close all my channels and run away screaming at this point?
I think I gave that away already. I don't think so. What we found is that there is an issue with centralization in the Lightning Network. We found that by analyzing the public graph, we could analyze that the most central node, like one node, is included in 50% of the payment paths. We did network simulations. We sent simulated payments between random nodes. We found that the most central node, one node, is included in half of the payments and observes that something is going on. That doesn't mean that they directly know who's sending to whom, but they have the information that somebody is sending to something and they know which amount is being sent roughly, or at least at their point, which amount is transferred. And of course, that gets quote unquote worse from that. For example, 4 nodes can observe 72% of all payments. This kind of centralization issue was known already, that there are tendencies towards centralization in the Lightning Network and that they may have some kind of impact on privacy, because some nodes see a lot of payments, they have a lot of information. The question is, on the one hand, decentralize that, and on the other hand, are there mitigations toward that? Can we increase our trust level into certain nodes? Can we change the routing algorithm to not use the shortest path? So all these mitigations that we can discuss in a bit more detail, they always come with a certain cost to the user. I think it's at that point for the community to discuss us which kind of mitigations are worth the cost and which kinds of mitigations we can maybe even do at a technical level. With regard to actual de-anonymization, we found that, at least according to our simulations, if you control roughly 10 nodes or more, you have a 50% precision and 50% recall of identifying senders and receivers of payments correctly. All the thousands of nodes in the Lightning Network, you give a best guess who was the sender and who was the receiver, and in half of the cases you are correct, to abbreviate it in that way.
What that makes me think of is LN Big. Do you know who LN Big is?
Sure, we actually analyzed them.
Perfect. Do you think that LN Big in particular is a bit of a risk with the subject that you just spoke about there?
In our paper, we analyze 3 possible scenarios. That is, one, we looked at the most central nodes in the network. We increased the number of central nodes, so the most central nodes we analyzed, and looked at how precision and recall of these attacks scale with that. We also looked at random nodes in the network. So if you were an adversary that would control just some number of nodes in the network and they are scattered somewhere randomly, how good would you actually fare in that case? We had a look at LN Big mainly because they are simply really well identified by their name. This is not because we think that LN Big in particular is a specific threat, but because they are a big player basically, and they are easily discerned in the network because they have the right node alias. Especially that makes it a bit more unlikely, I would say, that they are an actual threat, because if you were to run actual attacks on the network, you would probably at least give each of your nodes a different name and not one that gives it away that they all belong to the same party. The other 3 scenarios we analyzed, we found that LN Big has actually quite decent precision of anonymizing senders and receivers in the network. That is mainly because they are actually not positioned in the network very centrally. They are positioned in a way that are more on the fringes, so they're covering the network really nicely. Let's put it this way. They have a high probability that a random sender and receiver is close to them, in contrast to the really central nodes that are really at the center of the network, which can be from a random node in the network quite some hops away. We found that to be the case, that because of this, LN Big has quite a notable precision. So we found it could potentially de-anonymize nodes with something around 70%, but it has quite smaller recall. So it actually doesn't see all that many payments, especially if you account for them having 26 nodes in the network. If we're looking at that 26 nodes, the most central 26 nodes could have a quite a bit larger recall. So they see a lot more payments, therefore have a larger recall of nodes and larger recall of source and target nodes that were correctly de-anonymized.
That's very interesting. It's basically a good argument for saying that LN Big is not the person we should be worried about, because the adversary on the Lightning Network potentially would be smart enough not to name all their nodes the same thing and would be far more devious than that.
Yeah, on the other hand, that's what I also said about the trust. The question is if at some point in time, especially if you have these pretty central node operators, if there shouldn't be some kind of process, I wouldn't say auditing, but some kind of way that the community tries to get to know who's actually running these really central nodes. And it would be possibly an idea to give users the chance to configure who they are actually trusting, and at least say, okay, if my payment could go over these channels, I would prefer them to other nodes that I don't know about who is running them. This could be a potential mitigation, even though one that is usually not liked by many people, because introducing trust into such a decentralized system is often a thing that is correctly more or less frowned upon, because we try to minimize trust in these systems. But especially looking at the current Lightning and payment channel design, we have these semi-centralized node operators and everybody can participate. So maybe we should try to infer how we can actually start to trust some nodes in the network that is hopefully not infringing on privacy and not doing these attacks.
I've said for years now that it might wind up being necessary to pretty much bake a web of trust type dynamic into Lightning in order to really make it work at scale. I mean, ultimately, a payment channel, it is very trustless in the sense that if it's executed properly, can handle something on chain and have it arbitrated to a correct outcome. But there's still the degree of trust in that relationship that like don't cause me a headache and like try and dispute things on chain. I personally would rather we don't go that way. I would like to see every other potential solution explored. But at the end of the day, if that's the one that works, well, I'm okay with that then. That becomes part of the trust trade-off of this system.
That would be a possible road towards mitigating such risks. Let's put it this way. Even though you said web of trust, this is also kind of frowned upon concept because it failed big time with PGP, for example. Nobody used PGP, and especially nobody used the web of trust part for it, apart from some really technical people, but it never got to a decent point.
I mean, I think that's more of a usability thing than the actual technology itself. It's just that one, it was done at a time where technology penetration was very small in society. And two, it was never really made that easy for people.
I agree with you. It's a usability thing, but I think it's generally really hard to actually communicate to somebody that's not really technical what they're actually doing when they say, I trust this person. So what are actual consequences that arise from giving somebody the green dot and not the red dot in the user interface? That's really hard to explain that to somebody who doesn't know how the system works. Educating users and then building really great UI to actually go into this direction could potentially solve some of these issues PGP had, but I'm not sure that it's entirely mitigated by it. But maybe we should come back because it's really like a
kind of a tangent.
Yeah, that's a kind of a tangent. This was just basically one idea we had. Actually, introducing trust is not the central point. When we look at our attacks, there are certainly also some caveats that have to be looked upon that were just introduced with our model. Our simulations, so the numbers that we just said, so precision and recall of the anonymization, of course, always consider that every payment is using a shortest path algorithm for finding these paths. We re-implemented basically the algorithm that LND uses pretty closely, actually, which is an algorithm that's used, an extended version of the well-known Dijkstra's algorithm for finding shortest path in the network graph. The attacker now in the network, so the malicious intermediary, can only de-anonymize or identify senders and receivers under the assumption that they are routing payments over the shortest path, or let's say over paths that are generated by something like LND's algorithm. When we now start to introduce paths that are longer and that are irrationally longer, for example, we make some of them randomly longer, we don't always use the most efficient route, that would require the user to pay a bit more fees because the paths get longer, not the most efficient route, but it would lead to a depreciation in the accuracy of the attack. If some implementations would introduce some kind of randomization techniques, they could potentially mitigate to some degree at least these kind of de-anonymization attacks. How much they actually can do that and what impact that would actually have on the numbers, I don't know. We just would have to see that. We have to re-evaluate that and have a look on how good this scheme is and how good the randomness is. But this would, for example, be one possible mitigation. Of course, that would introduce some kind of tax on the user because they would have to pay more fees. And similar mitigations would be, for example, especially towards timing attacks, would be to introduce random delays, maybe even in the payments, which I think is a rather bad idea because that would basically conflict with the rapid payments that Lightning tries to provide. You could think about many ways that you could build such a latency model and then use this latency model when it sees a specific payment to then infer who sent it. However, with regards to building such a latency model, the way we proposed was, as you stated, was that the adversary would run a certain number of nodes in the network and then would try to send payments over all channels in the network that are, however, bound to fail. By measuring the time it takes to fail these payments, they would be able to measure each channel individually, how much time it would take to send a payment over it. This is how we propose in our paper to build such a payment model. So to counteract this kind of measurement study that the adversary would do, introducing some kind of latency or some kind of delay in the failure messages would be an option, a randomized delay, and that would at least mitigate using maybe our exact way of building the time difference model we use for this kind of de-anonymization attacks. There are other ways how you could try to infer a sensible model. This would probably reduce the accuracy, and then the adversary would try another way of building such a latency model. So it's always an arms race, you see. What can the adversary do and what can we do so the adversary has a harder time?
All right, so I teased you guys before we started recording. I think here is a perfect point for this. A very shy friend of mine who doesn't want to put this out there quite yet because this is still a half-baked idea, has an idea for solving this at the payment level scope rather than trying to enforce something at large in the whole network. Obviously, as a timing analysis attack, the core way to defeat this is just add artificial latency. What if you did that, extending the bolt spec for HTLCs to do this on a payment by payment basis? So let's say you want to enforce added latency that you create random different values for each hop. Well, what if you took some subset of the payment details that you're passing along the payment path and encrypted a subset of that, leaving enough in the clear that there's a reasonable certainty this is a real payment, but in order to get the entire payment payload, you would have to decrypt something. Two ideas that my buddy had are either using a time lock puzzle, so like something that was pre-generated with a seed and then hashed thousands of times to get to a key that was used to encrypt that subset of the payload. Also, you could do maybe some kind of key stretching thing where there is a key passed along in common and a random salt to stretch it that they would have to brute force. Either way, if you extended the bolt spec to allow nodes to opt in to something like this, then a single payment could protect itself against this type of attack by having this kind of added latency on each hop actually enforced through some kind of cryptographic method just for that payment.
I think that's an interesting scheme, actually. And this would, of course, enforce a certain latency. Of course, if you opt in on a per payment basis, you are basically saying, okay, I'm now forfeiting the quick response and I'll accept that my payment is delayed for a certain amount of time and I can even enforce that it's delayed. That's quite a nice idea. Of course, that would entail that suddenly node operators would have a lot more work, especially in the hash time lock puzzle. They would become something like micro miners where they need to hash a lot until they are able to process these payments. And of course, then you introduce all the issues, all the economy scale issues that you have with mining. Some node operators maybe can afford or want to spend more money on better hardware and would be able to run these time lock puzzles quickly. So the delay is maybe even negligible and they still solve the puzzle basically. And others maybe run on a Raspberry Pi and would take for ages to solve a puzzle. Then you have a huge delay. While I think that's a really neat idea, I'm not sure if it's not introducing a lot of issues again, maybe even complicate things that don't have to be complicated. Maybe it's even enough to just have some minor randomization on each implementation.
It's definitely something with a lot of nuanced angles to it, but my thinking is that even with the economies of scale, nodes would opt into facilitating this type of payment rather than just, no, I'm not going to relay this because part of it's encrypted. And so there's that kind of opt-in aspect to the costs of it. My thinking about the economy of scales are, as long as you don't overshoot the difficulty too hard on some of these things, well, if you find the right balance, then it's okay the Raspberry Pi chugs along for 5 seconds and some big industrial node in the middle cracks it in like 50 microseconds. There's still some delay introduced along a subset of the hops in the overall route.
Theoretically, you could even also introduce something when we are already applying like a mix scheme. We could think about applying something like an actual mix scheme to some degree. So there's something like a timed mix scheme we know from the area of mix networks. And the idea is you batch together all messages that are coming in a certain time slot. You only forward them in a randomized order after a certain amount of time. Maybe you can do something like that to batch messages together and then introduce these kind of randomness. I think I read somewhere that C-Lightning is even doing some message batching to a certain degree, although I'm not sure if they are actually batching together payments or if they are only batching together channel updates.
That's an interesting direction. I hadn't even thought about it.
Quick question that I have on my side here, if you guys don't mind. It seems like a bit of a naive question, so forgive me if it is, but would multi-part payment factor into this at all?
We don't had a really big look into multi-part payments, but we also discussed that in our paper. From what I understood, that is the current design. If I'm not misinformed, the idea is that every part of the payment would still have the same secret value. So they are basically all correlatable. So everybody who observes multiple parts could see that they are all belonging to the same HDLC. The thing with multi-part payments in this case would be that by splitting up the payment amounts over multiple payments, you would improve the privacy in terms of the amount. Adversary sitting in the network couldn't as easily infer which is the overall amount that is transferred. Only if she would observe all the parts in the network, all the payments, she would be able to do that by reassembling basically the payment. However, because the payment is split up over multiple payments, there are a lot more payments overall to be observed. In that regard, multi-part payments could even be a bit detrimental with regards to privacy because there's just more information for the adversary that is potentially observed. If you're splitting a payment that was before, quote unquote, only one payment, you had a certain chance that in the path you're choosing, a malicious node is included. Now you're splitting the same payment over 10 different paths. Suddenly you have a higher probability that at least one malicious intermediary node is included. It could even be that this first multi-part payment scheme is a bit detrimental to this kind of privacy. However, there have also been other schemes for multi-part payments, especially there is a paper that introduces anonymous multi-hop locks that would allow to decorrelate these payments. Each payment would look different in each hop. This would at least in part mitigate that because every part of the payment would look differently and the adversary would not be able to infer that they all come from the same source or go to the same destination.
Are there any other mitigations or any other things like that we should jump into here?
Two assumptions we introduced in our research is one, when we talk about de-anonymization, we assume that identifying a node, that means we can see where a payment originated or where it's going to is actually de-anonymizing the user. This is only the case when somebody is running on their real IP network and you assume that you have some kind of associating your IP address with your real identity. Of course, if you run behind Tor, for example, if you run your Lightning node on a hidden service, this may change. So you could still maybe associate from which Tor node, basically, from which hidden service a payment came and where it went to. This doesn't maybe reveal who's actually behind it. You should, of course, use Tor if you can to anonymize your Lightning node. However, it doesn't solve everything, of course. Depending on the intention of the adversary, maybe it's not even the idea to identify a real world person, a real identity, but I don't know, just inferring who is sending how much to whom and that it's interesting to you out of other reasons. And maybe then it's for you more than enough to know that this Tor node you associate with some kind of identity is sending to this other node. Just using Tor is surely not solving everything.
Wouldn't that depend on how often a node was changing Tor circuits? Like if a Lightning node on Tor were to start regularly moving things through different circuits and switching that, couldn't that potentially break the latency map the attacker constructed?
This is most likely the case. So if you are switching circuit very quickly, this will probably break the latency map. And so the attacker has to redo the latency map and refresh it over time. We didn't really analyze how often this would be the case. On the other hand, interestingly, because each hop in the Tor circuit is often really far apart, or the whole circuit introduces quite a big latency, it could even be that in that case that running over Tor gives your node more particular latency. So it's bigger and it looks different than other nodes because you're running over a specific circuit. So maybe your node is even in terms of latency a bit more discernible, but we haven't really analyzed that. That is just something we're thinking about. That could be the case. However, in general, if you then reconnect, of course, over Tor, that means that you would need to rebuild your latency model. In general, we looked at the public channel graph. One future research we want to really have a look at is how we can extend or how to do timing attacks or these kind of attacks on hidden channels, because in our simulations and our from attacker model, we're only considering public graphs so far. With the capability of having hidden channels, this this gets, of course, a bit more complicated because all the reduction of feasible candidates I talked a lot about, the adversary wouldn't be able to do that because he or she simply doesn't know all the candidates if you have hidden channels. This would be a future research area of ours that we really want to look into if you can use something that's called topology inference to figure out if there is a hidden channel. Using hidden channels is inhibiting our attack.
We are reaching the end of the show here. Shinobi, do you have any final questions you want to throw out before we end the show?
I'm kind of plumbed out of questions. I think this was pretty fun. Elias gave me a bunch to think of that didn't occur to me until this.
Yeah, ditto.
Thank you. I had fun too. Thanks.
Elias, before we do close out the show, do you want to let the listeners know how they can find you on the internet, find the paper that you wrote and all that?
Yes, of course. The paper is called Counting Down Thunder, Timing Attacks on Privacy and Payment Channel Networks. I think the easiest way of finding it is here in the description, or you just Google it, or my name. You can reach me via email. That is elias.rohrer@tuberlin.de. You also find that on the paper if that was too quick. You can find me on Twitter. That's _TNULL. So T null with an underscore in front of it.
All right, perfect, Elias. I want to thank you for joining me on the show. And I also want to thank Shinobi for being my guest co-host on the show. It was really cool to have you, man. You asked a lot of questions that I would not have even thought about, so I really appreciate it.
Hey, man, it's fun. I just want to see you keep making awesome content about the Lightning Network.
Gotta tell people why it sucks so much, right?
Not broken.
Not completely broken, just a little bit.
All right. I think we're going to end it there. Once again, thanks to both of you guys, and I hope everyone has a good rest of your day.
Boom! That was the 33rd episode of the Lightning Junkies podcast.
I definitely feel like that episode was cut short far too quickly. I was limited on time, so I was not able to have the full conversation. It's very ironic that shortly after this conversation ended, Shinobi and Elias ended up having a separate conversation in which they discussed big blocks briefly and how Elias thought they were a bit of a mistake. And even though he saw this issue on the Lightning Network, he still saw big blocks as a dead end. If you learned anything from the podcast, we would appreciate you supporting us. You can learn the different ways of doing this by going to lightningjunkies.net/support, where you can find all the different ways to support us, including all the podcasting platforms you can find us on, the different ways that you can tip us using Bitcoin and Bitcoin over Lightning. You can even tip us on Strike. You can subscribe to our mailing list at lightningjunkies.net/sign-up. You can check out our memberships at lightningjunkies.net/membership. Finally, you can check out our store at store.lightningjunkies.net. Hopefully that's enough stuff for you guys to check out and for you to support the podcast with. We're definitely going to be bringing more shows like this that are going to be heavily skewed towards skepticism. We're also going to be adding, or a new show rather, that's about newbies. Newbies. I love newbies. That'll be our Jolt series that you will see very soon. Stay tuned. It'll be fun. It'll be great. I'll see you there. All right. I think after that long, you are surely sick of hearing my voice. So for now, I shall see you lovingly on the Lightning Network.